programs. Okay? In that problem set, there's an analogy that I'll do in a more simple way here on the board that's done in a lot of different books you can find. And you'll get the idea of this conundrum. So there's a town. I always think of the old Andy Griffith show because there's that guy, Floyd the barber, and everybody hangs out in Floyd's shop. And here's the deal. In this town, the barber shaves everybody that doesn't shave themselves. Okay, everybody get that? It's a fairly simple idea. If you shave yourself, you stay at home. If you don't shave yourself, you go to Floyd. There's one barber in town.
Are you talking men or women?
I'm talking everybody. Floyd's got a nice job. Alternatively, the town's all men, but we want to keep it interesting. Okay, so if you don't shave yourself, you go to Floyd. So the question is, does Floyd shave himself or not?
Is Floyd male or female?
Floyd's a male. Well, I guess well, all right, let's not go down this road. Does Floyd shave himself or not? If you shave yourself, are you supposed to go to Floyd? No. So if Floyd shaves himself, he's not supposed to shave himself. That possibility doesn't work out. But if he doesn't shave himself, what's he supposed to do? He's supposed to go to the town barber, namely himself, to shave himself. So you can't answer that question, does Floyd shave himself? If you say the answer is yes, the answer should be no. If you say the answer is no, the answer should be yes. So this implies that the statement that I made at the beginning doesn't make any sense. Right? That's a strange little conundrum. It seems like one of these stupid little puzzles somebody throws at you in a bar and you just say, please go away from me, I'm meeting a friend. Right? It's like, or can I buy you another drink? Here. I mean, but it's actually at the heart of maybe the most important theorem in theory of computation, that there are programs that you can't write. Programs that, things you want to compute that there are no programs for. And I'm going to get back to the example I did yesterday, but this time we're going to nail it down in a relatively more rigorous way. So let's say, here's what I want to do. I want to convince you that there's no program that will find infinite loops in other people's programs. Remember I mentioned that there's no such program that does it. I'm going to convince you of this today, and it will bear a little bit down on that barber analogy, but we're going to see it in the diagonalization way. You'll see it in your P set with the barber analogy, but we're going to see it here in diagonalization. So I tell Donna, when you go home tonight, do me a big favor, and for homework, when you're all done with the problem set, because I know you'll have plenty of extra time, why don't you go ahead and write me a program that finds infinite loops in other people's programs, and bring it in tomorrow. All right? And she likes a challenge, so she comes in and she goes, I have it, here it is, and she gives it to me. So we're going to assume now, proof by contradiction, we're going to assume now that she's done it, that she's come up with such a program, and I'm going to convince you that she's lying. Okay, is everybody with me? All right, so here's... Oh, well, there's a contradiction. All right. Yesterday we talked about a table where I number all the programs in the whole world, that answer yes or no to their inputs. And I put them here, and I number them 1, 2, 3, all the way up to infinity. There they are, every single program in the world. No programs are missing. They're all there. Okay, there's no program that's missing. All the programs are there. There may be things we want to compute that there are no programs for, but we'll find that out later. Right now, all the programs are listed here, and we list them up here as well. And we fill in this chart in the following way. We run this program on this input, on this program as input, and we see whether it says yes or no. Now, yesterday we had a little bit of a fudge factor. The question was, well, how do you know if it says yes or no? Right? Maybe it doesn't. And I said, well, you could always check if it says yes, because you could dovetail the computation. But then the issue is, well, if it never says yes, there'll just be question marks, and we kind of got stuck. And I said, don't worry, you'll see it again. And I said, well, they're just going to worry, and let me show you what really happens. Today we have Donna's program, right? Nobody worried. Today we have Donna's program. Donna's program will tell us whether a program goes into an infinite loop or not. So here's...
That's what all these programs do, right? They return a 1 or a 0 when given a program.
All they do is say yes or no to a given program, like a compiler. Yes, this is good. No, it's not good.
Okay.
Okay?
So her program is one of those?
Should be, right? Right, her program's one of those. Right, her program's here. D for Donna. Donna's program is here. That's a good point. Chris is right. Donna's program's in this list. It takes programs and it says, yes, do they have infinite loops, or no, they don't have infinite loops. Okay, by the way, we hope Donna's program run on Donna better tell us that it has no infinite loop, right? I hope so, right? Otherwise, your program is baloney. So we know there's a 1 there. Yeah?
So when you run a program in a program, what we're determining is if that program with any other program in existence as input will or will not have an input.
When I run Donna's program on another program, right, it's telling me, does it ever go into an infinite loop?
No matter what the input is.
Right, right. Does it sometimes go into... Well, no, I'm sorry, Rob. Her program will take the program and any input at all you want and tell you whether it goes into an infinite loop.
It takes 2 inputs.
It'll take 2 inputs to your program. Right. So I guess but we can make a version of Donna's program in here. We can make Donna's program just check if a program accepts itself or not. And then Donna's program would be in our list.
Okay.
Okay? So some version of Donna's program is in here, D prime. And that's not the main part of this idea. But let's continue. All right. So here's this list. Let's start filling it up with the help of Donna's program. We'll take program 1, run it on itself. Donna's program says this is not an infinite loop. So we let it run for a few years, and sooner or later it says yes or no, I accept or I don't. If it says I accept, I'll put a 1 here. If it says I don't, I'll put a 0. So let's say it doesn't accept it. It says no. I say 0. It says yes to 2. Now what happens here? I throw in program 1 on input 3, and Donna's program says, hey, this is going to be an infinite loop. So what should I put in, a 1 or a 0? It's just the choice. And we're going to do 0. If it says no, we're going to do 0. If it's an infinite loop, we're going to do 0. But if it says yes, we're going to put in 1. Okay? We're not going to distinguish between infinite loops and saying no. Infinite loops and saying no are both going to turn out to be 0s. All right. So in this way, I fill in this whole table. I can fill it all in as long as I go.
And we defined, we set some time limit on determining whether or not something is an infinite loop, and therefore we give it 0, or what?
Her program just can do it.
Her program does it. That's our assumption. I sent her home last night with this job. I'm going to convince you she's lying, but she says she's got one that does it.
Okay, so first we run her program on everything to determine whether it has an infinite loop.
And then we fill in these
And then
values.
those that don't, we actually fill in these values.
Right. But the ones that do, we just write zeros in.
Yeah.
Okay. Questions so far? Everybody okay? All right. All right. Here's the next step. The next step is what we did yesterday. You've seen this before. I am now going to go down the diagonal, and I'm going to convince you that there's a row in this table that you missed, that there's a missing program here. But this time, I want to analyze what that program is actually doing. Here's the missing program. I'm going to go down this diagonal, and I'm going to toggle all the bits. So here's what I get. I get 1, 1, 1, 1, 0. This row could not possibly be in my infinite list. If it was in my infinite list, what would happen?
Toggle one of those bits.
Right, it would not agree with if it was, say, in the 15th row, it wouldn't agree with the 15th spot in that row. This particular value that I just created is different than every single row that's already in the table. It's different from the 3rd row in the 3rd spot. It's different from the 80th row in the 80th spot. So this is a new row that was not included in our list of programs. This is a computation that we have no program for. Well, what is this computation doing? What does this program, if I could write it, if it existed, what would it accept? What are these ones representing? They were the old zeros, right? This program accepts all things that either say no to these inputs or else are in infinite loops to these inputs. Right? That's what this program does. And this program doesn't exist. But it wasn't in our list. But I'm going to convince you this program, everybody agrees now, doesn't exist. It wasn't in our list. But what would it do if it did exist? It would say yes to every single computation that ends up saying no to that value or going into an infinite loop. Now that we agree this doesn't exist, I'm going to convince you that Donna's assignment last night implies that this does exist. Donna has something that checks for infinite loops, right? She can take any program and any input and check if there's an infinite loop. Well, I could just take her program and fiddle with it a little bit and make a program that does this. Here's what I do. I take her program. It checks for infinite loops. I'd run this particular program on a particular input. If it was an infinite loop, I'd put a 1 there. If it's not an infinite loop, I just run the program until it sooner or later tells me yes or no, and then I know what to put in the next spot. I could compute this line if Donna's program worked. I wouldn't have any trouble writing this program. But this program doesn't exist. There is no way to write this program. It doesn't exist here. So the fact that Donna said she had a solution has got to be wrong, because if she has a solution, I can write that program. All right, this is a very subtle, tricky idea. This is actually a completely, relatively rigorous way of showing it. You need to let it sink in a little bit. Here's the moral of the whole thing. If you try to write a program that accepts all other programs which say no to themselves or infinite loop, that's impossible. You can't write a program that takes another program and an input and tells you whether it's an infinite loop or says no. You can't write a program that does self-hating. All right? Programs are not smart enough to know about themselves. They're smart enough to know about a lot of other programs, but if you include themselves in the group, they lose their power. Floyd can shave everybody in town that doesn't shave himself, but if you include him in the town, he loses his great perspective. Right? So this analogy...
Where does the self come in with this? Where's the self reference in this?
Because if you think of what this line actually is, it's all the programs that infinite loop on themselves or don't accept themselves. Why is that? Program 1 on itself, either infinite loops or doesn't accept itself, so I put a 1 here. Program 2 on itself, either infinite loops or doesn't accept itself, so I put a 1 here. Program 5 on itself does accept itself, so I put a 0 here. This computation is trying to figure out which programs infinite loop on themselves and which ones don't accept themselves. This is a computation of all self-hating or infinite looping programs.
Okay.
Do you see where the self thing comes in?
I see that.
Okay. So if Donna's program actually works, I could build something that does this. I take Donna's program, I put a program into it, I run it on itself. She tells me if there's an infinite loop. If there is, I put a 1 here. If there's not an infinite loop, I just run the program on itself until I get an answer. And if it says no, then I put a 1 there. If it says yes, then I put a 0 there. So I could use Donna's program to construct this, even though we know that this particular program is impossible, because it's not in our list. Yeah?
I apologize if you addressed this before, but why can't you just pick a vertical row or a horizontal row and make the same argument? Why is everything doing that? Why is it
Like
just the diagonal?
maybe all right, that's a good question. What if I just took this horizontal row and I toggled all these bits and I tried to claim to you that row does not exist here?
Or what if you just toggle one of them?
Well, if you toggle one of them, it just means that it's different from this row.
Okay.
But it might be identical to one of the other rows. There's no guarantee it might not be somewhere else in our list.
Since they both go on to infinity, it can't be identical.
Here's one that is identical.
Yeah, but it may not be identical at the infinity end.
It's identical except for the first one. Right?
Okay. Which is
So if you're so this one is different from that one, right?
right.
But now I'll have another one down here, which is say this, well, the same one. This could have been here. If you just concentrate on one row and you create this, say I just changed the first bit of that row. So I get this new computation. And you're trying to convince me this row is not anywhere else in the whole. But here it is. I just showed you. It was number 6. I just didn't write it in before. The idea of this diagonal argument is that there's no row that could ever be further on.
All right. Well,
So-
we won't argue about one bit, but even why not take a whole?
I'll switch the whole thing. Good. That's the next step. So how come I can't play this game with a diagonal idea, right? It seems like I'm just cheating here, right? You say it's not there because it's different than that. When I say it is there, it's number 8. You just didn't see it. So how come if I go down the diagonal, it can't be number 8?
Well, how do I know the diagonal is not a row? I can't see that at the bottom anyway.
Because it can't, because it differs from the diagonal in the.
This row number 8 is going to be different
At the point 8.
at that spot.
All right.
So I know that it couldn't have been there.
But it's almost like by definition we're projecting into infinity.
We are. look, if your sense of this proof is that it's tricky and magical, it is. It is a tricky and magical proof, and your first gut instinct might be not to trust it. But your next instinct would be to spend 100 hours thinking more about it and trying to see how it all fits in with the Barber conundrum and putting it all together. And it really happens to be a deep proof. There are no flaws in this, and it really does work, even though it seems tricky.
Are you saying it doesn't work for a row or a column?
It doesn't work for row or column, but it does work for the diagonal. Because if I do this trick and I say, oh, it was number 8, I just didn't show it to you, you can say, well, that's baloney, Shai. It can't be number 8 because when I constructed this value, I constructed the opposite in this row, so it couldn't have been row number 8. But if you just change this one, I can tell you, well, it's number 8. It's just the opposite of that. It's when you construct something down the diagonal that you know it's got to be different than all the rows that are already there, because it hits all those rows. You could, you don't need it diagonally. You could do like knight's moves would be okay, probably. And anything that, it would be a little bit uglier to do the proof, but anything that hits all the rows in unique places would probably be all right. Yeah, John?
I'm a bit confused about whether the finite and infinite thing. I thought we started from the basis that however large the number of possible computer programs is finite.
Oh, it's not finite. It's countable.
Okay.
It's countable. That's different than finite.
Okay.
It's infinite, but it's the same infinite as natural numbers.
Yeah, yeah.
Okay?
And this list is all possible computer programs?
Yes. Right. Right. And if you want to say, okay, well, I didn't have the, sorry, I thought I had the list, but now that you mention it, I should have put this one in there. Then I'll put that in there, and we'll do the whole argument again. And I'll come up with a new one.
But we could arrange it so that it's every possible computer program and a lot of junk.
Yes. Typically what you do is you actually take your characters that you make programs out of and you order them lexicographically in alphabetical order. And any ones that actually don't make legitimate programs, you just define those programs to be the programs that just do zeros all the way. So you might get lots of rows that are zeros, and that would be the junk you're talking about. But that wouldn't affect this argument. It would still work.
And this argument just works with infinite loops? That seems to come out of nowhere.
Well, because we're on the diagonal, so it's programs working on themselves. And the idea is that you can't figure out whether programs accept themselves or not. And the part that falls apart is the part whether they're infinite loops. Because if it always terminated, then we could fill out any of these values and actually have it as a program. So the only thing that really prevents us from doing it is that infinite loop idea. I should say that what you do in theory of computation is you take this problem and then you reduce it to a gazillion other problems, some of which are very far from this. So one very important problem, this is an extremely important problem that is completely unable to be done, is what if I give you, it's a fancy word, but it basically means a compiler. What if I give you two context-free grammars? If I give you two compilers, this is a compiler for Scheme, this is a compiler B for Scheme. Two people did it. They're competing. They want to make a good compiler or a better compiler. And the question is, I'm giving you these two compilers. I want you to just make sure before I test them against each other that they really do the same thing. That they're both compilers for Scheme. That they both accept the same things and reject the same things. That problem, taking two context-free grammars or two compilers and deciding whether they do the same thing, is not decidable. In other words, nobody can write a program to do that. That's a really important program to be able to write.
That seems kind of strange. Well, you couldn't document.
Because why couldn't you compile the one program with the other program and then run the program through that and make sure you get the same output?
Well, to check that you'd get the same input, you'd have to run it on the infinite number of possible inputs to check that they'd all be the same. That's the brute force way.
But what I'm saying is if you took the one compiler and compiled the other compiler with it, all of the outputs by that compiler should be the same as the outputs of this compiler, and then they would be the same.
But that doesn't cover all the cases.
No, I don't think it would necessarily be the same. If you run one compiler on a bunch of Scheme programs and you run another compiler on a bunch of Scheme programs, and there's an error in one of them, it's not going to be the same. If you run one compiler through another compiler, then the first compiler, if it has errors, is going to have errors when you run it through the second compiler, and the second compiler would work fine. That wouldn't help make any distinction between the equality here. One could still work fine and the other could still mess up, even if you're going to run one through the other. So, I mean, it's true one can simulate the other, but neither one can know whether those answers are all going to be the same.
But if you then reversed it, right, and ran it through, you would notice your errors would come up.
Yeah, after an infinite amount of time. Say the error say there's no error. How do you know they're always going to get the same answer? You keep running and running and running, and you have to keep trying. Well, nobody knows any better way in any case. So there is no algorithm that's guaranteed to finish that tells you yes or no through all the cases. Yeah, Rob.
But compiler behavior is totally deterministic. The compiler behavior is totally deterministic. The crux of that problem is on...
Compiler behavior is deterministic, but in order to check whether they're exactly equivalent, we'd have to actually run the two compilers on every possible input.
But you couldn't determine whether compiler A was exactly equivalent to compiler A unless you knew for a fact that they were the same compiler.
That's true.
So
That's true.
So isn't this
There is no automatic way to check that you have something that really works.
puzzle that there's no way to fully document the behavior of a compiler? So as a result, you can't document the behavior of a
You could check for a particular compiler whether it worked, but not for a general one. There's no program that will take anything and tells you whether this really meets the specification that another program is describing. Okay? There are more specific ways of specifying what a program should do, and you could check those, but you can't just take two arbitrary context-free grammars and check whether they actually accept the same things or not. That's impossible. But this is a theory of computation discussion that we should have like in 4 months and not today. So we should. But last couple questions. Yeah, Brian and then Sam.
I'm just imagining a case where the compilers only differ by, say, 2 lines of code that we can isolate into certain languages.
In particular cases, you might be able to narrow it down to a finite number of cases, and you're right. But your program would have to work on any two compilers. And the point is that it can't. It might be able to, if you could restrict your problem to a simpler subset of compilers, it might be able to work. But if it has to run on any two, it fails. So that's a good point. Yeah, Sam.
Your proof depended critically upon the fact that there were a countable number of programs. Suppose the number of programs is not countable.
But it is countable. I can show you how to count them.
But
Any universe of programs is countable?
Yeah, because programs are just a sequence of characters. Every program is built out of characters, and every program has a finite length. Therefore, I can count all the programs in any language. But you're right, it is dependent on the fact that programs are countable. Programs are just syntactic structures. What isn't countable is what programs can do. The things programs can do is uncountable, programs themselves are countable. And that, in a nutshell, is why there are things you want to do that there are no programs for. Okay? I want to do something now that's a little less fun, and you just need to see it, because if I don't show it to you in class, you'll say, "Did you do that in class?" And I'll say, "Well, I didn't do it because it was boring. I wanted you to look it up." I'm going to do it real quick. It talks about functions. We talked about functions yesterday. You need to know a few definitions about functions, things that computer scientists and mathematicians take for granted, and things that you probably may not know, and I don't want you to take it for granted. So let me go through these definitions and explanations, and it has to do with the idea of making a one-to-one correspondence, showing that something's countable, and what a one-to-one correspondence means. Because a function is not always a one-to-one correspondence. So I want to talk about that for about 10 minutes, and then I'm going to shift gears, and we're going to go back to sums. I'm going to show you how to evaluate sums when there's induction involved, how to evaluate sums when there's no induction involved, and we'll work our way towards recurrence equations. All right, so functions. Functions and one-to-one correspondence. Let's stick with one-to-one correspondence first, because I hope you know what this means. A one-to-one correspondence is some sort of a correlation between a set of things here and a set of things here, where every single thing here corresponds to a particular thing here and vice versa. So here's a one-to-one correspondence. We did this one yesterday. The natural numbers to the positive even integers. Okay, 1 goes to 2, 2 goes back to 1. 2 goes to 4, 4 goes back to 2. It's a one-to-one correspondence. The function that represents this one-to-one correspondence is f of x equals 2x. Anytime you have a one-to-one correspondence, you have a function that represents it. Now, what's a function? You're all supposed to know this, but I'm just going to review it. The only thing that has to be true to make a function is that it's got to be a rule. It's got to take something and transfer it to something else. But the one thing that it can't do, it can't change its mind. Okay, if it takes 1 and decides that that goes to 2, then it can't take 1 and send it to 3 the next time you send in 1. So if it was a machine that has a little hole and you put the input in and then the output comes out another hole, every time you put a little ball that has 1 on it into that machine, a 2 better come out. If you put 1 on it the next day and a 3 comes out, then that's not a function machine. Send it back to the company that makes function machines and say you want it to fix it. Okay, it doesn't work. Functions can change their minds. All right. Yeah, question?
But it's still considered a function, like if you say if it's 1, make it 2x. Like if it's less than 1, it's 2x. If it's greater than 1, you can make it 3x.
Sure, because it still has a unique answer for every single input. Right, you could make it into lots of different cases if you wanted to. Right, sure. All right, if you have a one-to-one correspondence, then not only is this direction a function, but the inverse direction is a function. That's the forward direction. What's the function that goes backward? We'll call it g of x equals x divided by 2. And we sometimes write that, this. G of x is the inverse of f of x. Okay, it's the backwards. It's the thing that sends you back. Some terminology. If you have a one-to-one correspondence, then a function has an inverse. There are functions that don't have inverses, and there are functions that are not one-to-one correspondence. And we need to talk about them, and there's a couple definitions, and I'll do some examples, and then we'll let it go. Okay. Everybody okay so far? So here's an example. When you talk about functions, you need to say where the input's coming from and where the output's going to. That's called domain and range. Month 0. Good. Here's a function. It takes x, it sends it to x squared. The domain are the natural numbers. The range is the natural numbers. Okay, so this function takes only whole numbers greater than 0, and it sends them to other whole numbers greater than 0. Is this a one-to-one correspondence? It is, right?
It's into, it's not onto.
Is it a one-to-one correspondence, yes or no?
Yes.
Yes, I say it is. I'm trying to get you to say yes. Now I'm saying no. What is it? Let's see what it means. Let's write it down. 1 goes to 1, 2 goes to 4. If I make this range go to natural numbers, then there are some natural numbers on this side, and if I put them in to my inverse function, or if I try to go backward, what happens when I put 3 in here? I don't get a natural number on the way back. Right? 4 goes back to 2, but 3 goes back to the square root of 3, and you know that there's no whole number that's the square root of 3. So this function doesn't have an inverse per se going from n to n. If I made this r to r, real numbers to real numbers, then, well, we'll do that. Well, but it's a different reason.
So what was the question?
From n
Is
to the
this,
squares of the
does this have an inverse? Was that the...
That's the issue. Does it have an inverse?
Does
So
it have to have an inverse to be one-to-one?
a one-to-one correspondence and having an inverse are if and only if. They're the same.
So if you didn't define it as natural numbers to natural numbers, it might have a one-to-one correspondence.
Right. Your choice of domain and range affects whether something has an inverse or not. Affects whether it's a one-to-one correspondence. You need to know what the domain is and the range is in order to answer this question. That's right, Tony. Good. All right, so let me do an example and explain a couple of definitions. There are 2 definitions for functions that functions can be. And if they're both of these, then they have a one-to-one correspondence and they have inverses. The 2 things that make you have a one-to-one correspondence and an inverse is when a function is 1, 1, and when a function is on 2. This does not mean the same as a one-to-one correspondence. Both of these together imply a one-to-one correspondence. This is a separate idea and this is a separate idea. Let me explain what these are. They're not hard ideas, but you have to get the terminology. A function is on 2 when every single value in the range has something that gets sent to it, when there's nothing left out. So is this function onto? No, it's not onto. It's missing lots of values. 3 doesn't have anything sent to it. 5 doesn't have anything sent to it. 17. I like to think about this in the following way. Here's a picture. Here's a domain. That's onto that I just did. Here's the range. A function sometimes is written like this, where we take something from the domain and we move it to something in the range. Here's a function. Let me ask you a question about any function in the world. Is there ever more than one arrow coming out of this dot? No, that's what a definition of a function means. One arrow coming out of this dot. In a function, is it possible to have dots here that are empty? Yes. But what about an onto function? No. So an onto function means everything in the range has to have at least one arrow pointing to it. And that's how I like to think of it. At least one arrow. To everything in the range. At least one arrow to everything in the range. You could have more than one arrow. This guy could go here also. It's possible. A function is 1, 1 if you have at most one arrow coming in. At least one arrow to every dot means it's onto. At most one arrow means it's 1, 1. I think that's the easiest way to look at it. It's not the typical definition, but it's virtually equivalent. At least one arrow, at most one arrow. If you have at least one arrow and at most one arrow to everything in the range, what does that mean? Then every dot in the range has exactly one arrow. That means you can reverse the arrow orders and you get a function, right? If you reverse these arrows, do you get a function? No, because you got two things coming out of here. If you reverse the arrows and you have an empty one, then that's a problem because this is in the domain now, and there's nothing in the range that it would get sent to.
Wait, so it's 1 to 1, even if two different locations, even if two different values from your domain point to the same in your range. No?
No. 1 to 1 means there's at most one arrow. I'll give you an example of a function that's 1, 1 and not onto, and a function that's onto and not 1, 1.
Okay. So
I'll give you examples of all these things in a second.
But you can have a reverse function even if it's not onto, right?
No, you can't.
Can't have
Because if it's not onto, Chris, you've got this empty.
Is this example with the squares?
This example with the squares. It means you've got lots of dots here that have no arrows pointing to them. So when you go back from this domain to this range, a function has to tell you what to do with everything that you throw in the input. So when I throw this dot in, it says, sorry, I'm broken. And that's not a function.
Didn't we define onto or 1 to 1 though as being, it means you can go, it has a reverse, has an inverse 1 to 1 function?
No, there's a difference between a 1 to 1 correspondence and a function being 1, 1. They're two different things. Yeah. I know it's a bad choice of words, but that's what it is for 100 years, so tough luck. 1, 1 is different than a 1 to 1 correspondence. A function is a 1 to 1 correspondence when it's both 1, 1 and onto. Okay?
So
yeah.
The way you could reverse the function is if you change the domain to squares of natural numbers. Yeah. That you could.
Fine. Anthony suggests that instead of calling this natural numbers, we'll call this the squares of the natural numbers, in which case this would be onto and 1, 1, in which case you would have a 1 to 1 correspondence and you'd have an inverse. That's true. And that's what Tony was getting at before, that you could change domain and range and fix some of these problems. But let me do a couple more examples so you'll get more of this. So here is a function that, as it's written now, is not onto, but is 1, 1. Right? There's no two things here that go to the same one on that side. So it is 1, 1, but not onto. 1, 1, not onto. Let me do another one. Ceiling of x, that means if it's a fraction, it just raises it up to the nearest integer, to the whole number. And this goes from the real numbers to the natural numbers, or to the integers. We'll include negative numbers. Okay, so any real number you have in the whole world can go in here, and we just push it up to the nearest integer that's bigger than it. Is it onto?
Yes.
Right? Because it gets every possible integer. Is it 1, 1?
Couldn't possibly be.
Couldn't possibly be. There's a gazillion real numbers, 1.2, 1.4, 1.7, 1.8, that all go to 2. So this is onto, but not 1, 1. How about the...
Possibly be because the reals are on top.
Right. What about this function? Real numbers to real numbers. I take anything you give me, I add 1. Is it onto?
Yes.
Yes. Is it 1, 1?
Yes.
Yes. So this function should have an inverse. What would the inverse be? Right. Has an inverse. It's a 1-to-1 correspondence. When Tara did that countable argument for pairs of numbers, and she did that diagonal thing, you know, did she do that? All right. So when she did that, she came up with a function. That function should have been a 1-to-1 correspondence, and it should have an inverse. You give me a number, I'll tell you where it is in the chart. You tell me where you are in the chart, I'll tell you what number that connects to. Okay. Questions about this? Yes, Sharon.
Did we define onto as, sorry, every point in range is mapped onto?
Yes, has at least one arrow, right.
Where do we account for the fact that if we inverse everything in the domain needs to have been mapped from? Is that covered by 1-1 definition?
Here.
Because if we reverse and our domain then becomes the range, where are we accounting for the fact that when we reverse everything that in our foreign domain has to get mapped to?
Because there's always, for any function, an arrow coming out of every dot in the domain.
Okay, so we can't have more things in
You can't have empty things in the domain that are left open. That's part of the definition of a function. Not only can't you change your mind, but you can't say, I don't know what to do with this input. If you give me the domain, that means you're willing for me to put anything in it. Okay, that's like a candy machine saying, insert nickels and quarters, and nickels are fine. And then when you insert the quarter and you press your Hershey's bar, it says, sorry, you know, can't take quarters at this time, right? So, yeah, right. But that's a bad function, right? That's yeah. Well, that's a busted machine. Here, one more example, real fast. Here's a function. Okay, a finite function. 1 goes to 1, 2 goes to 1, 3 goes to 3. Is it onto?
Nope.
No. Is it 1, 1?
Nope.
Nope. Does it have an inverse?
Nope.
Nope.
Can you write that function?
Yeah. Here's how you write finite functions. The domain is the set 1, 2, 3. The range is the set 1, 2, 3. Here's the function f. F of 1 equals 1. F of 2 equals 2. F of 3 equals 3. Oh, yeah. Thanks. Yeah, so you can write it. I just can't, right? Right. A finite function you can write by just specifying the things. We're used to writing functions as formulas, and you think of a function as a formula. But a function is not a formula. A function is any kind of correspondence between a domain and a range. And if it's a finite set, then you can always describe it by just listing it.
What if you have something like x equals 2 and your range is all integers? Would that be not either one?
If your range is integers, then 2 is supposed to go someplace. I don't understand.
All the arrows point to 2.
Oh, if all the arrows point to 2?
Yeah.
That's okay. We can do that. That's still a function. Oh, I see. Then you can write f of x equals 2, yes. Instead of writing f of 1 equals 2, f of 2 equals 2, f of 3 equals 2. It's also not 1, 1. It's also not onto, right?
Wait, quick erase it.
Yeah, I'm not erasing it. Just look like I'm going to do it. That wasn't what you were thinking about. Yes.
You wrote down the range was 1, 2, 3.
Right.
Is the range still 1, 2, 3, even though the original is rolling?
Yes. It's like you got to decide if you're punting or not on 4th down before, well, in a kid's game, before I set the defense. You got to decide what your range is and specify that and then tell me what the function is. You can't just say, oh, my range is whatever I'm going to hit to. And if you do, then tell me your range is that, and I'll exclude 1 and 3 from the range. Okay?
The interesting thing is the book switched the definition. They called the codomain the set of all possible values, and the range the set of values that are actually hit by the function.
That's what Sam just said.
Oh, I thought Sam said
No. That's what you just said, right?
The codomain was actually hit.
Oh, no. The range is the thing that's, well.
I mean, it's just a technique. But I
Yeah, but you'll notice I did not use the word codomain. Yeah. So, this is not a pipe. Right. Here's a. Oh, geez. Anyway, I like to give you as few terms as you need to actually understand the idea. And sometimes that's 0. Sometimes. Okay, a couple of quick things now for a little bit of review in orders of growth with functions. Oh, we got a lot more. We're going to do 2 examples just because there's one problem on the problem set that I think is really crucial for experimenting with and for learning about orders of growth. It's the problem where I gave you a gazillion functions and I asked you to order them. I said if they're big theta of each other, put them on the same level. But if one is actually, larger than the other, say small o of the other, then actually put them in order. It's a really, really useful problem because you have a lot of pairs of functions to compare, and it will force you to develop intuition that you wouldn't normally get by just doing the everyday typical examples. So here's a simple example of the kind of thing that might come up on that problem, and then I'll do a harder one. The question is, how do these compare to one another? And the answer is that they're the same and they're both x log x. They're both big theta x log x. And let me show you why. You all should know this, but I'll show you why anyway. Log of x to the x equals x log x. So it's certainly big theta x log x because the constant is just 1 for both cases. It's less than or equal to x log x where the constant's 1. It's greater than or equal to x log x where the constant's 1. That's one of those log rules you learned in month 1. What about this one? This one is x times 2 log x, which equals 2x log x. So that's going to be big O of x log x because it's less than or equal to 2x log x. And it's going to be greater than or equal to x log x for a constant of 1. So you can big O and big omega. So this is also big theta x log x. Intuitively, the constant doesn't matter. So x log x and 2 log x are the same. These 2 functions are the same. And you'd put them on the same line. All right, let me do a more complicated example. You're probably thinking, oh, gee, I wish I really had absorbed all those log rules. And you would be right. The more those are automatic, the faster you're going to be able to have a good guess as to which function is. And when they're not automatic, it's going to seem like you're working hard. But the harder you work, the more automatic it'll be the next time. So here's a hard one. Or a harder one, at least. X to the log x to the x. I just reversed them. 2 different ones. Yeah. We're going to compare them. Which one's bigger than the other? Are they the same? What are they compared to? So at this point, when you're a beginner, you just look at it, oh, geez, I never saw anything like this. Did we ever do anything like this? It's not fair to put this on the exam if we didn't do anything like this in class.
Oh, no, now we're doing it in class.
Uh-oh. Look at this example. You need to be able to compare these 2 things. They don't look very easy to compare. If you have some intuition mathematically, you probably already have a good guess as to which one is harder. But if your intuition is still at a beginner's level or even an intermediate level, you might not know where to go. So let's try to at least get this into a better form. Let me give you a goal. If it looked like this, would you have a guess which one is bigger?
Nope. Oh.
This one looks bigger because this exponent is bigger than that, and these are just a factor. Whether they actually are, one's bigger than the other, maybe they're big theta, you'd have to work through the definition. I should mention, as a good thing to remember, that when you have exponents that are the same, if this is bigger than this one normally as a function, it's big O, it's a larger specifically than this, then this whole thing is larger than this as well. And that's something you could prove, and in some of the exercises you end up discovering this yourself. But it doesn't look like that. We have to make it look like that. We have to make it so that we have some chance of doing this.
Take logs on both sides.
Take logs on both sides. Yeah. What base? Any base you want?
Any base you want, but this is base 2, let's make it 2.
Okay. What Sam is suggesting is more or less what I want to do, but I like to present it in a mildly different way. So here's what I'm going to say. I want to introduce this in a slightly different way because it relates to something you'll see in recurrence equations, the idea of changing the variables. Changing the variables and making it look a little more like what you like. And it's essentially equivalent to taking the logs of both sides. Why am I going to make this substitution or this change of variable? Because I'd like it to be 2 to the something versus 2 to the something, like I showed you before. So let's go ahead and do this and see how things simplify. And if you're thinking, how would I know to do it? Well, you guess, you try some tricks, you get better at seeing which trick works. It's not very satisfying, but that's the best I can do right now. Let's try to calculate x and log x so we can substitute in there and change everything to y, change the variable. X is 2 to the y. We chose that as our substitution. What is log of x going to be? Say base 2, y. Now the logs are gone. You know, logs make you sick, so get rid of them. So x to the log x, what does that look like? 2 to the y to the y. And comparing it to, what's this? Y to the... It still doesn't look quite what we want, but if I had given you this to begin with, you probably wouldn't have had a complete horrible knot in your stomach, just a mild one. Look at these two. They're different from the two we started with, but they are still relatively comparable. I just changed the variable. How can I compare these two now?
You have 2 to the y squared and y to the 2 to the y.
Let's look at this one. 2 to the y to the y is the same as 2 to the y squared. Okay, 2 to the a to the b is 2 to the a times b. How can we write this in terms of 2 to the something? Is there any way? This y, let's say I wanted to take y and write it as 2 to the something. It would be 2 to the what?
2 to the log y.
Again with the logs. 2 to the log y is y. That's the definition of log y. 2 to the log of y is equal to y. So I substitute that for y. And I still have the 2 to the y up here. So what's this equal to? This is not equal. This is a question mark. 2 to the log y to the 2 to the y. Let's finish it up. It's 2 to the log y times 2 to the y. So now I've got what I promised. We got 2 to the something equal 2 to the something. And let's compare y squared to log base 2y to the 2 to the y.
I didn't quite get that last step as quickly as Sam did.
2 to the a. That's a good point. 2 to the a to the b is 2 to the a times b. Okay, it's the same step we actually used here. 2 to the y is 2 to the y squared.
How did you get the 2 to the...
2 to the log y equals y. That's the definition of what log y means. This is exactly the definition. There's no idea there except the definition. Log y is the number that if you raise 2 to that number, you get y. And I just put it in there. So the rule of thumb is you can always get rid of a y and turn it into 2 to anything you want. So we did that. We forced it. I twisted the arms of these formulas until they looked the way I wanted them to look. And I hope to God when I was all done that the exponents would be something that were more obviously comparable than what I started with. So let's look at the exponents now. Here I have y squared. Here I have 2 to the y times log base 2 of y. Which one's bigger? Don't take too long. You did this. Which one's bigger, 2 to the y or y squared? 2 to the y kills y squared. It's a mismatch.
We're taking a log of it.
No, it's log base 2y times 2 to the y. No, this is just bonus. This is like take this huge guy, in I don't know, the Goldberg guy, that wrestling guy, right? You take a huge guy, that's 2 to the y, put him up against me in the wrestling rink, y squared, just some typical average guy, and then give Goldberg like somebody to tag in an extra log y as if it wasn't enough just to have 2 to the y. This just kills this. There's no match. Right, boom, right. Head into the turnbuckle. All right, what's the point? Therefore, this one is bigger. And if this one's bigger, that means this one's bigger. 2 to the y squared versus 2 to the log y times 2 to the y. Compare this to this.
And that's log 2y times 2 to the y. It's kind of up there, so it looks like it might be another.
It's times, right. That's what Chris was saying before.
So what order would you say this is? 2 to, if you had to use big O notation?
Well, we haven't said that at all. All we said is that this one is definitely going to be bigger than this one. But if you wanted to put it back into big O notation, we could say that this is, order, every function is order itself. This is order 2 to the y times log y. But if you wanted to put it back, you'd have to redo this, and we just end up getting this. So the idea of what it really is kind of like, it's not really a well-defined question. It's not like every function is big O something unique. They're big O of all the other functions that are larger than that. So you don't look for some canonical one to compare it to. You just compare it to another one. Typically, we like to put all functions into one of typical, like n or n log n or n squared or 2 to the n. I mean, these are the ones that come up so often. So we tend to like to take any weird thing that comes up and figure out where it sits relative to these. But that's just because these come up a lot. There's nothing really special about that. I want to talk about sums. I want to talk about this sum in particular, and I want to connect it back to your problem sets. We're going to talk about sums. We're going to work our way to recursion, back to sums, and then say goodbye to sums and logic and all this stuff and move on to a different topic as of tomorrow.
Which topic is that?
Recurrence equations and recursion. Today's going to overlap right now in this. You've done a bunch of proofs by induction. Some of you definitely get the idea. Some of you are kind of on your way, and some of you are like hate the idea and don't get it yet at all. And you all will get it, but it'll take some time. Some problems, I say, are screaming for induction, and some problems, I say, are not so natural. And if you get that idea, you probably know what I'm talking about. And if you don't get that idea, it just seems like, what's he talking about, screaming for induction? So I want to give you an example. In one of the problem sets, I show you a particular theorem about cubes. That's the theorem, right? This is a theorem, again, from that same medieval math book back in the 1321. Levi ben Gershon proved this theorem, and he proves it by induction. And if you look in your problem set, what he discovers before he proves this theorem is another theorem which just lends itself to discovering this. Does anybody remember what that other theorem is? Anybody do this yet?
N cubed.
What's the theorem he proves?
Oh, that
N cubed plus the sum of the...
each term of the n cubed is that minus that.
Well,
Is that n plus 1?
I believe you know what it is, but now the question is, can we state it?
It's 1 cubed plus the triangle numbers up to n minus 1.
He proves something like this. What does he say this is equal to? Does he do this? No, this is not what you mean, right? No.
It's one term.
Because if there's one
n cubed plus, that's how we know.
Excellent. And I think that's what you were trying to say, Chris. You go up to n minus 1 and you square it, right? Plus n cubed. And what does that equal? Something like that, right? Is that right? And he proves this with algebra. He proves it's not so hard to come up with this. Let's make sure it's right before I say it's not so hard to come up with it. I think that's right. Good. It's definitely right. He proves this. He comes up with this in algebra. He discovers it one day. When you discover something like this, all you got to do is look at it for about 3 more seconds to say, oh, if this equals n cubed plus this, I'll just do it again. What does this equal? N minus 1 cubed plus just do it again. And you can do it again and again. And what happens? This stays on the right side, and this keeps disappearing, turning into cubes, one down as you go, until sooner or later, you get to the base case, the thing that stops you, and you get 1 here at the end. And that's where this comes from. This theorem is a screaming induction theorem from the discovery of this theorem. It's just natural. It's recursion. It's all the stuff you did last month. You want to figure out, you want to solve this for n? Do it for n minus 1 and add n cubed. What happens then recursively? You do it for n minus 1. You add n minus 1 cubed. You call the recursion again. It's exactly recursion. So he discovers a recursive theorem or a relationship like this, and that implies a bigger theorem, a more interesting theorem. Anything like that is a theorem that's screaming for induction, and anything like this is a theorem that's kind of screaming not to do induction. There isn't any natural theorem like this that looks just as clean for this example. So if you actually look into Levy's book and see what he does, he has a long sequence of other completely complicated algebra ideas to come up with this formula. Even though you can bet he understood that he could have done this by induction, he just thought it was a terrible way to do it because it was badly motivated. Here he did it by induction because this is the way he was motivated to solve the problem. Here he didn't do it by induction because he didn't think that this was a nice way to do it. So we're going to do this today. I can tell you what the formula is here. It's equal to this. We're going to calculate this formula not by induction, although we could do it by induction. It's just some algebra. In fact, if you want to practice it, it's another good example to practice induction on. We're going to do it by a completely different method. This method will not only show us what I mean by a different kind of a proof, but it will help you learn a really important thing, how to manipulate sums. Manipulating sums is a crucial thing to be able to do in the analysis of algorithms. And in manipulating sums, at some point, the dot, dot, dot notation isn't quite good enough or quite helpful enough, so we end up inventing something called a sigma notation. And in this proof, you're really going to have a need for it. It's just too hard to do this without the sigma notation. And up till now, I haven't introduced it because I think it just makes people have a language barrier to the idea. But in this proof, we're going to need it because the language is really necessary. I'm going to avoid it until we absolutely need it, and then I'll introduce the notation. Here's how we start to do this problem. I'm going to motivate it a little bit. The first thing we start to do is we notice this particular series if you add up the odd integers up to some point, you get square numbers. People knew this, documented, back 300 CE, the late Greek period, people knew this. It's not so hard to discover this. You can discover it geometrically. Here's 1. Here's 1 plus 3. Here's 1 plus 3 plus 5. Everybody see what's going on? Every time you add the next odd number, you just wrap around the next shell of the square. It's kind of a proof. You could prove this by induction. This does scream for induction. Let's say that all the sum of these add up to n squared. What happens when you add one more? N squared. You add one more, what do you add? You add 2n plus 1. That's the next odd number. And what does that equal? N plus 1 squared. That was such a fast proof by induction that I left out all the gazillion steps that you would really need to put in to make it completely clear. But the gist of this proof, if you would go ahead and write it clearly, which I'm not going to do right now, maybe I'll come back and do it later. You probably could use the review. But the gist of this proof is adding on the next number to a square gets you the next square. And if you could write that out clearly step by step with the base case, etc., you'd have a proof by induction of this. But let's just assume this is true now, and we all know it's true. We're going to use this to get this formula. So let me stop for a second. Questions so far? All we have is these odd numbers adding up to squares. We're going to come up with this in a couple of minutes. Everybody okay? Here we go. Here's my list of squares. 1 plus 4 plus 9 plus 16 plus, What does this one turn out to be? N squared. Let's check to make sure that's true. If n is 3, the last term is 5, and I get 3 squared. Right, so the last term is 2n minus 1 here. If I add up these numbers, I get the sum of the squares. What Levy did is to add up these numbers by adding up these numbers, but add them up a column at a time. Here are the squares. Just add them up, but change the rows and the columns. Is everybody with me so far? Stop if you're not. Questions?
Wait, the n is 2n minus 1?
Yes.
Because like what's n in the case of 1357?
In the case of 1357, the n is going to be 4, and that's equal to 16. 4 squared is 16. Okay. Let's add these up. Let's add these up. Here's where not having good notation gets a beginner to the point where they give up, and having good notation smooths the mathematician right by. How many ones do we have here? Everyone agree? 1, 2, 3, 4, 5, all the way up to n. Is it true? Yeah. N times 1. How many 3's do we have? N minus 1 times 3. How many? 5. N minus 2 times 5. N minus 3 times 7. All the way down to the last case where it is 2n minus 1 times 1. How are we going to add this mess up? So here's where we need a better notation to help us add this up. You might be able to avoid it, but I don't see an easy way to avoid it. What I want to do here is notice how the first term here is changing and how the second one is changing. Here's the notation that we're going to use. This means the sum of. We're going to start with 1, 2, and figure out the first term and the second term. When n is 1, what's the first term? It's n. Second term? n minus 2, etc. What about the second terms here? This is 1, 3, 5, etc. When I'm up to the ith term, what is this one going to be?
N plus 1 minus I.
What's this one going to be? Is that right? Let's see what this is. When I'm at the first term, it's n. When I'm at the second term, it's n minus 1. It's always n minus the number that's 1 smaller than this. So it's n minus I plus 1. Okay? If I'm on the fourth one, this would be n minus 4 plus 1. That's n minus 3. Fourth one, n minus 3. That works. Here's the general term of the first one. What's the general term for this one?
2i minus 1.
When you're at 1, you're at 1. When you're at 2, you're at 3. So double it and subtract 1. What I'm really doing here is multiplying those pairs as I starts at 1 and goes all the way down to, what's the last one that I goes to? Starts at 1 and goes down to, or goes up to, n. So here's how we write it. I starts at 1, goes up to n, and we're going to add up all these terms. n minus I plus 1 times 2i minus 1. Now I could have done this using the dot notation, but it would have been a little bit uglier. This really summarizes what I just said. We have these two pairs of things that are multiplied by each other. They change their values as I changes from 1 to n. When I is 1, they should be n and 1. When I is 2, they should be n minus 1 times 3. So if I just want to add these up, I'm adding up this sum. And you're thinking, well, what's the point of writing this like this? How does it help? It helps a lot if you can think about what's going on and unravel this. So we're up to here, and we're about to finish up. And it gets a little bit hairy, but here's where you have to learn how to manipulate sums. If you can learn to manipulate these things, you'll be doing great. Okay, other questions so far before I finish with this? Questions? Good. I'll make some room here so we can actually manipulate this. And I'll keep our goal up here so we can keep track of where we're headed. Here's what we're going to do with this sum. We're going to do what you always try to do, even without any particular good intuition. We're going to multiply these things out together. If we multiply them out together, then we have the sum of the first plus the sum of the second plus the sum of the third. We can split it up into separate sums, each of which might be easier than the sum of this product. So let's multiply it out and see if we can split it up into smaller pieces. What do I get? Let's do it. 2i n minus 2i squared plus 2i minus n plus I minus 1. Minus n plus I minus 1. Let's see if we can fiddle with these things a little bit, make them simpler if possible, and then do the sum of the ones we need to. I'll rewrite it up here. Okay, EJ, simplify this a little for me. What goes together?
You could make it, you could get rid of the plus 2i and plus I and just make it plus 3i.
I'll go for that. Plus 3i, yeah, what else?
You could...
Anything else?
2 times n plus 1 times I.
You're combining this one and this one?
No, the 2i and the 2ni.
2i and the 2. You're going to combine this one and this one.
Use that term already.
Oh, I'm sorry.
Oh, yes. Okay. Okay. Why don't we do the minus n and the 2in then?
Okay.
So then we get n times 2i minus 1. Does that look okay?
Isn't the...
Do we want that?
I'd rather group the i's together.
Okay. So 3i, 2in. What else is left? Constants. What's left? Minus n minus 1. And then we got this ugly thing at the end, minus 2i squared. Is that all okay?
Yeah.
Let's double check it, make sure it's all right. All right. Well, let's look at all these pieces. Some of these pieces can still be a little bit more combined. Let's take these and group them together because they both have i's in them. 3 plus 2n times I minus n minus 1 minus 2i squared. And now let's look at it and see what we get. What happens when you add up minus n times for I equals 1 to n? There's no I in this picture, right? That means minus n, minus n, minus n, n times. What does this turn into? Minus n squared. See how easy it is to sum this piece? It doesn't have an I in it. Start getting used to the following intuition. If you see something inside a summation sign and a piece of it doesn't have this variable in it, then just multiply it by how many times you're doing it. So here's what happens. We still have this piece here. I equal 1 to n of 3 plus 2ni. We still have this piece here, the minus 2i squared. But out here we're going to take the n squared, and out here we're going to take, what happens to the minus 1? Minus n, because it gets done n times. And that stuff is now out of the summation. I took it out. It's all been summed. The only thing left to sum is this thing that has an I in it and this thing that has an I squared in it. Let's keep going. We're almost done. I should tell you that Levi does not do this with algebra. He does this with words. So if you can imagine, it's hard enough to see this in algebra. If you can get through it in words, you really understand it.
We can do the summation that multiplies
All right, before we do that, we are going to do that in just a second. I want you to look at this. What does this whole thing equal? Who remembers?
Summation of I squared.
Right? Don't lose track. Summation of I squared. Right? What is this?
Same problem.
It's the same problem, but twice. Right? Here's what we got so far. The summation of I squared equals this. So I'm going to take the summation of 2I squared and move it to the other side of the equation. I'm going to pull it out. How many summations do I have here now? 3 I squared summations. And on this side, all I have left is minus n squared minus n. Everybody see what I did? This is the most clever spot. I'll explain it again. This is the most clever point of the proof. On this side, I have a summation of I squareds. In fact, I have 2 of them. They go from I equal 1 to n. That's exactly what the whole formula equals. So I take this summation of 2I squared, and I add it to both sides of the equation. On this side of the equation, it cancels this out. And on this side of the equation, I get 2 more summations of I squared.
It would help if that was separated into its own sigma notation.
Put 3 notes. Put 3 sigma notation. The I squared, the I is a
Chris suggested this, and I think it's a good idea. I'll split these into 2 different sigmas so you can see that they're both supposed to be summed up. This one needs to get summed, that one needs to get summed. Now I'm going to take this and add it to both sides of the equation so it moves to the other side. And now this side gets to be 3 times the sum of I squared. Other questions about that?
You can take out, that's not really in the same form, so you can take out the 2, right?
You can move the
You
constant
can move the 2
outside
in front of the sigma notation even.
If you have 2 in front of here, it can move out right in front. Right.
fair,
Right. Sure, that's fair because it's just getting, each term is getting multiplied by 2, so you're essentially just factoring it out. Right.
This
Yeah.
is just the same trick we did with integration by parts for sine and cosine.
Yes, it should remind you of that trick. Yes, that's a good point. Right. It's very much like that trick. When you do integration by parts, you get the integrals in terms of another integral that's half the size, and then you pull it back over, and then you get that constant term. That's true. It is just like that trick. All right, and we're almost done here. We got the square root of, we got I squared sum from 1 to n. We got 3 of them here. What we have to do is sum this, and then we can divide by 3 and get an answer. Does this look familiar? The 3 plus 2n is like a constant. That gets multiplied by each one of these i's every single time you go from 1 to n. So it just can get pulled out and factored out. It does not depend on I. Look at this. Ever see this before? Those are triangle numbers. Adding up I from 1 to n. 1 plus 2 plus 3 all the way up to n. Here's what we get. The sum of I squared from 1 to n times 3 equals 3 plus 2n. What's the sum of the numbers from 1 to n? N times n minus 1 over 2.
N times n plus 1.
N times, I'm almost with you. Right, n times n plus 1 over 2. Thank you. Good. At least my notes are right. 3 plus 2n, n times n plus 1 over 2 minus n times n plus 1. That's the right-hand side here. If you put this over a common denominator, what do you get? This is 3 plus 2n times n plus 1 minus 2n times n plus 1. So it's going to be 3 plus 2n
Minus 2.
3 plus 2n minus 2 times n plus 1 over 2. 3 plus 2n minus 2 is the same as 2n plus 1. And if I divide through by 3, I get a 6 here. So the final answer is 2n plus 1, n plus 1, n divided by 6. And that is the same as the way it's written there. All right, so that's a long, long, long manipulation of a sum. It's a great example of manipulating sums, and there's nothing in this manipulation that doesn't consist of the following things. If you get the sum of lots of things, you can split them into the sums of the pieces when they're added or subtracted together. If you get a constant or something that doesn't depend on I on the inside of your sum, you can pull it out in front of the sum as if you're factoring it. All of these symbolic things you have to get used to are just transferences from what you do in algebra. But think about it intuitively and stop making the intellectual connection. When you stop making the intellectual connection, you immediately get used to the fact that if I see pieces multiplied inside the sum and there's no i's in those pieces, I can pull them out. If I see lots of pieces inside the sum that are pluses or minus together, I can split them into smaller pieces. Get used to those manipulation rules, and you'll be able to work faster with these summation signs than you will with a dot, dot, dot notation. All right, questions about any of this? That was a good question. All right. Well, there's actually no complicated idea here except for the notation of the sum. Maybe Sam will go over this in recitation today at 4 or 5. What do we say? 4.
Getting it into the sum notation seems kind of.
You mean writing it like this and making?
Going from the original 1 plus 2, 1 squared.
Oh, this part. Yeah, no, that's the hardest part. You're right, Doug. That's the hardest part, is going from that table to the sum notation. Because if you can't do that, you can't manipulate the sum at all. You're right. That's the most important thing. I think if Sam goes over this slowly at 4 o'clock today, anybody who didn't get it here, I think would benefit a lot. It's important to get good at this kind of thing. So if this seemed like a lecture from the clouds the last 20 minutes, then definitely go see it again. Gary.
Could you write it up and give us a hard copy? It doesn't have to be nicely.
I got it. It's online.
It's on. Okay.
Yeah. Yeah, I can't always say that, but today I can. Let me think. Wait, did I really do it?
Does this help?
I probably did. I got to go check. I'm not sure how far I am in typing my lecture notes, but they might be there. They're certainly written here. Yeah.
Does this help you work with infinite sums?
Yes. Well, Tara's going to do a bunch of infinite sums in the recitation. I'm going to do, I'm going to do some infinite sums. I didn't get to where I wanted to. I'm right on time, but I didn't get ahead of myself today. The next thing I want to do is move over to recursion and recurrence equations. And the first thing we're going to do is that Towers of Hanoi problem that you did last month. And in doing that, we're going to come up with a sum that'll be an infinite sum, or at least looks like an infinite sum. And we'll cut it short at some point and make it finite. And I'll show you how to add up geometric sums. And from geometric sums, we'll do things that are similar to that. So big picture. This is the sum of the squares. You did triangle numbers. You did divergent and convergent series 2 months ago. All those things are part of summations, but it's a big, big topic. I'm just going to throw in the basics in the next couple days. We're going to do geometric series and versions of geometric series, which Euclid knew 2,000 years ago. So that's old stuff. And then, as we move into Towers of Hanoi, into other recursive stuff like your 7 rings problem, we're going to come up with all sorts of funny sums, some of which we will not know what they are until we actually experiment and do some cool stuff on the board with it. And that's why I want to make sure you can do that 7 rings puzzle, because you'll appreciate that lecture much more easily if you can actually solve the problem. So we'll continue with sums. We're going to shift over to recursion starting tomorrow. Tara will finish with sums today. Tomorrow she'll go over the exam. Right, that's our plan.